So I'd like to welcome everybody to Transform Solution breakout session titled Optimizing Distributed Energy Operations. Today, we're fortunate to have presenters Daniel Lazaro from OSIsoft, Tom Arthur from Dianomic, and Chris Swan from Dispersive. It'd be nice maybe if we can begin by having each presenter introduce themselves, starting with Daniel.
Hi, I'm Daniel Lazaro. I'm a senior technical program manager at the CTO office at OSIsoft, and I run or lead the open source program.
And Tom Arthur, I'm CEO of Dianomic. We're the creators of FogLamp, and contributed the code to the Linux Foundation Edge along with Eve, and in there it's called Fledge, and we'll be talking about that today.
And I'm the most recent member of the party here, Chris Swan, CRO at Dispersive. We're known for ultra-secure virtual networking, kind of the glue that pulls together a lot of the DER participants, the ISOs, the utilities, all together in a way that they can communicate safely and securely. And Tom, thanks for inviting us to join you today.
Well, thank you for joining us as well. I guess I missed your headshots. My apologies there. We'll have plenty of looking at you the entire time. Yeah. So this is just a high-level architecture. So today, OSIsoft, Dianomic, and Dispersive will talk about their solutions and how they fit into the market, what complexities they encounter, and how they scale their solutions at the edge with remote orchestration. So at this time, I'd like to start by handing things over to Daniel.
Thank you, Tom. So first of all, let me introduce you to OSIsoft. OSIsoft is the most trusted source of real-time operational data. We enable the collection, standardization, and federation of large volumes of industrial operational data across different verticals. We're implemented in more than 21,000 sites internationally. With over 2 billion streams and growing, we have been delivering consistent value for over 40 years, and we are continually innovating to bring new technology to operations. Data is widely acknowledged to be one of the most valuable assets in business. Data drives everything in industry and in our culture, and its use is fundamental to how companies compete nowadays. But not all data is the same. We would argue that operations data is a unique resource. The more people consume it, the more valuable it becomes. So why is this true for operations data? For companies that rely on high-value assets and processes for their core business, like manufacturing companies, utilities, discrete, critical industrials, among others, those assets alone are not differentiating. The data is. So now let's talk about how OSIsoft delivers extraordinary value across the industrial enterprise. Next slide, please. Good data leads to smart decisions, as opposed to garbage in, garbage out. But what does it mean to have good operations data? In operations, this means real-time, high-fidelity data available to the right people at the right time. It's in context that you see the big picture validated by others so that it can be trusted. Good data is reliable and secure. Moreover, it includes historical records and its origins for data provenance. Good decisions that result, ideally connecting daily operations with corporate initiatives. So now let's add analytics to the mix. Previous slide, please.
Oh, sorry.
Yeah, no worries. That includes advanced calculations and algorithms, artificial intelligence and machine learning techniques to describe, diagnose, predict, and prescribe. From this comes smart decisions and thus better outcomes. It's that integration of the smart decisions into a strategy that leads to a fundamental business change in how you operate. All of this resulting in data that can be fed back into the system, creating the cycle of continuous intelligence. This allows another way that shows another way that the value of the data actually increases over time. Next slide, please. So now let's look at an example in the power industry. Power companies are interested in predicting when transformers will fail. Otherwise, that's a hazard and a disruption to their business. Collecting good data at transformers includes runtime stats, voltage, load, temperature readings, and the metadata that allows you to perfectly describe what the transformer operational KPIs are. As engineers at a customer site were looking at failing transformers, they noticed that several of them would have erratic voltage fluctuation just prior to the failure. And so they decided to trigger off of that fluctuation. When they noticed a larger deviation than normal, they would send out a crew to see if there was something wrong with the transformer. If indeed there was an impending problem, they would schedule a maintenance to avoid that failure, thus shifting from reactive to proactive maintenance. The continuous intelligence piece in this cycle was applied when they discovered that this erratic voltage was a good indicator of potential failure. They added the streaming calculation for the standard deviation of voltage. So now, in addition to that existing set of primary data, they also started to fit in a standard deviation as part of that data set so that it can be acted upon. It's this constantly iterating and innovating on primary foundational data that leads to much better output, better results, and better outcomes. Next slide, please. OSIsoft also adds value by bridging the OT, IT, and business domains. This is challenging since they are very different environments with different culture, context, and language. For operations management, we provide security across domains using one-way trusts and tokens and securing operational data sharing. For business management, we enable rapid integration with business applications and accelerated analytics with normalized data. We bridge the IT-OT chasm through the lens of analytics. Next slide, please. In summary, OSIsoft PI system delivers real-time, high-fidelity operations data to people, applications, and AI ML platforms. Data from assets, sites, and organizations rendering on any client device anywhere. In our world today, the competitive winners will be decided by who drives the best, fastest decisions on a continual basis. That can be achieved by using continuous data to power continuous intelligence, which drives continuous improvement. Next slide, please. The PI system is used in the power industry by over 1,000 power utilities globally. 100% of all of the independent system operators and regional transmission organizations in North America, 100% of the 20 largest utilities in North America, and 73% of the top utility companies globally. We also have a strong presence within the reliability security coordinators and transmission system operators in Europe, where we continue to grow. The PI system has driven hundreds of millions of dollars of value for utility companies over 30 years. It enables your organization to focus on reliability, safety, regulatory compliance, while improving operational performance, and provides an end-to-end solution with more than 300 innovative partners. The PI system is the tool of choice for leading utilities around the globe that want real-time data and analytics from all their operations. Next slide, please. So now let's talk about the grid. The grid is in the midst of transformation by three main game-changing disruptions: electrification of large sectors of the economy, decentralized by the sharp decrease in cost of DERs, and digitalization of grid, meter, sensors, etc. These three disruptions act in a reinforcing and amplifying feedback loop. Now let's go deeper into each one of them. Next slide, please. Electrification is critical to long-term carbon goals. That includes electrification of transport, not only cars, but also rails, planes, etc. Increase of renewable sources affect forecasting and load management. Behind the meter has a whole new meaning with fully integrated households, some of them becoming prosumers that incorporate smart appliances. Next slide, please. Decentralization is triggered by distributed generation like rooftop solar, driven by prices going down and energy independence. Distributed storage to maximize pricing, flatten out peaks and valleys like the solar duct curve. Continuous energy efficiency improvements to lighting appliances, etc. And demand response provides an opportunity for consumers to play a significant role in the operation of the electric grid by reducing or shifting their electricity usage during peak periods in response to time-based rates and other forms of financial incentives. Next slide, please. Digitalization includes advancements in technology to enable flexibility and data collection. The number of smart devices and sensors is exploding, requiring device management solutions and security at scale. Network automation systems include distribution management systems, or DMSs, advanced distribution management systems, ADMSs, and DERMS, distributed energy resources management systems. New digital platforms add new functions like blockchain and other technologies like SCADA as a service. Change is here and it keeps coming. Next slide, please. So here are some definitions around DER driving the transformation of the grid. Those include distributed generation, multiple units in a single location, behind the meter generation, energy storage facilities, DER aggregation DERA as virtual resources, microgrids that may have the capability to island, cogeneration of heat and power, emergency, standby, or backup generation, or virtual power plants, among others. Next slide, please. And here are some of the top use cases in renewables and DER. Failure probability modeling helps increase performance. Dynamic energy management toward energy savings. Predictive equipment maintenance reduce downtime and maintenance cost. Demand response management, a strategy to reduce demand and adjust energy flow. Improving operational efficiency, optimizing asset performance, or predicting and maximizing solar electricity production and predicting wind turbine production towards grid planning are a few examples. Next slide, please. So if transformation in the power industry is here, why are so many companies stuck? Next slide, please. The answer is there is too much data that is too hard to access and too hard to understand, especially the renewable data. Next slide, please. So why is the edge important to energy companies? There is valuable data at the edge that is often stranded because it is beyond the reach of automation systems. For industrials, the edge is the boundary past which they have not instrumented their equipment or devices. At remote locations, solutions are required to handle unreliable network conditions. Some of these environments are too rough for traditional PCs. And with that, I'm going to pass it on to Tom Arthur to talk about solutions at the edge.
Thank you, Daniel. My name is Tom Arthur, CEO of Dianomic. Dianomic transforms industrial systems and processes by supplying 3 products today. One of them, FogLamp, is an open source industrial IoT framework for connecting all of the different machines and services and processes Daniel just talked about, and in some cases, running applications on the edge when necessary. Fogman, which is our management system, when you scale out these systems, you'll see some slides coming up where some utilities may have 1 million edge devices or more they have to manage. It's really the Comcast cable box problem all over again, but in utilities and maybe many times more. And then Fog AI, a set of utilities that enable one to run machine learning on the edge for equipment where that's necessary. Next slide. So this slide's a little redundant about what Daniel just talked about, but let's get a little more into the weeds. We believe that industrial IoT edge is unique in its requirements. And the main point that is unique is what does it need to get data from, and where does it need to process that data, and where does it need to deliver that data, has many challenges in industrials you don't find in retail or at home. So more specifically, when you think about the edge in energy, most of the edge today is already covered in a SCADA or a DCS system from an ABB or an Emerson. But you'll find because of the price of compute, the effectiveness of less expensive sensors, the ubiquity of networking, there are more and more and more and more assets not connected to the DCS or the SCADA system in energy. And a lot of the examples and use cases I'll talk about shortly are new and emerging and not connected to SCADA. And then, of course, are these new workloads that I'll just call IoT or machine learning. So all of these new workloads and techniques around machine learning are probably, and in most cases, too much processing to actually run across your SCADA or your DCS. So you need new tools, new networks, new reach to run these applications on the edge in energy. And then on the north side in energy, the applications that consume that data are unique. So starting with this box here, for convenience sake, I just call it the ISA 95 stack. So systems like the OSIsoft Pi server Daniel just talked about, they're in about 22,000 installations. About 80% of energy utilities in North America use them today as a historian. Most of those deployments are actually south of the firewall. They're not on in the cloud. They might even be south of a data diode. So that data from these new services needs to feed the current operational systems. And then, of course, like everybody else, cloud computing is starting to be used more and more, even in operations. And so as these different services migrate to the cloud, your edge technology needs to be able to support those migrations. Next slide. So Dianomic, working with OSIsoft, Google, Nokia, FLIR, and many others, starting about 3 years ago, started coding a set of open source tools that we call FogLamp, which are a set of microservices that I'll give more detail to in the next slide. And in that process, similar to ZEDEDA, strongly believe that this really is an open source community challenge, especially in industrials. In industrials, literally there are hundreds of protocols I've never even heard of, and tens of thousands of data mappings to all the different kinds of machines you find in industrials. And to connect all that equipment really does require an open source strategy and building of a community. So with that in mind, along with Google and OSIsoft, Dianomic contributed the FogLamp code to the Linux Foundation Edge project. And when you contribute code to the Linux Foundation, they own the brand. So today, in a GitHub repository with the Linux Foundation, you can find the project Fledge under the LF Edge right next to Eve, which is FogLamp open source. And similar, if you're familiar with the way Linux and Fedora work, Fedora you can get in the Linux Foundation Git repository, or you can get a binary supported by Red Hat called Enterprise Linux. So similarly, Fledge is open source, FogLamp is open source, and if you need a binary that is commercially supported, you can get that from Dianomic. Next slide. So specifically, what is Fledge and FogLamp? So it's a set of 5 microservices designed to literally collect data from any and all sensors. We don't have time to get into the architecture today, but there's a concept of a plugin where without rewriting a microservice, a mid-level engineer can add a new protocol, and even a non-engineer in scripting can do a data mapping very, very fast. So it can collect data from any sensor on the edge. It can transform and filter that data in flight as it moves from the sensor to the historian or to a cloud. Filters could be as simple as converting Celsius to Fahrenheit, or it could be a very involved application in a Linux pipe doing all kinds of transformations of the data. FogLamp then can buffer that data. In many industrial applications, connectivity may be poor, so you want to buffer that data to make sure you don't lose it, and then send the data once the network is restored. It has an event engine, so you can act on that data, and it can operate very sophisticated analytics on the edge, anywhere from a simple Boolean logic to a machine learning running TensorFlow Lite to do predictive maintenance on some piece of equipment. And then last, one more click, it can deliver all of that data to one or multiple locations, north or south of the firewall and or to the cloud. So in energy, specifically to this conversation, what are the unique connections you'll find that an edge technology, an industrial edge technology must support for a utility to use it? So, and I've talked about a little bit of this already, but for instance, historians are broadly used throughout energy today as a recorder of all of the operations in both transmission, distribution, as well as generation. And then of course, traditionally, most people know that you're running either a SCADA system from an ABB or an Emerson or a Schneider, or you might be running sensors from an Emerson across all types of different equipment. So an industrial IoT system must be able to route data to all of these systems or connect to all these systems. Otherwise, you'll end up with silos of data and all this data out of context. Next slide. In the edge, there are a lot of emerging new use cases, and Daniel talked about most of them, so I'll just briefly go over this, and then I'll get specific on the challenges and why open source is powerful and needed. So you'll be surprised that even in substations, even million-dollar transformers are often not connected to the Emerson SCADA system simply because points are too expensive. And then, of course, distributed energy resources, exactly what Daniel just talked about, is starting to emerge, where you have protocols now where you get to the converters, and how does the utility actually manage the generation of that electricity when it's so distributed. And then you have new metering technologies from buildings and cities and so forth that the utility must have access to. And then, of course, all kinds of new non-SCADA equipment and remote equipment not connected to the current control systems in energy. So next slide. And to give you a sampling then of what an open source technology needs to support to solve these use cases in energy, just that substations, for instance, you need to support the protocols of OSIsoft, Emerson, Siemens. You can go ahead and click through this slide. GE, and then you have the standard industrial protocols you think of, like Modbus or DNP3. And if you can click, Tom, there we go. So right now you can see in this stack, all of these green check marks are current plugins and supported protocols in the open source stack FogLamp today. And that's because of the open source strategy. This demonstrates how open source really is the new standardization mechanism to make these connections happen. And so we're really proud of this happening. The yellow check marks you see right there are actually current companies that Dianomic is helping with the Linux Foundation create new protocols necessary for these different use cases in energy. So all of these will also be open source and available to everyone to use going forward. Next slide. So when you think about just staying on energy and the edge, and you can click through this, you can rapidly see where if you're starting to instrument the substations with equipment that aren't connected, you think of distributed energy resources where every community and every household's producing electricity as well as using electricity. You see the next generation of meters taking place for the utility to actually understand who's using what, where, and when, and all kinds of new workloads around machine learning and so forth. Quite literally, utilities will have hundreds of thousands, if not millions, of new industrial computers that they need access to and manage. And that's exactly why we're working and proud to work with ZEDEDA, who is managing the hardware and the operating systems in this equipment, while at Dianomic, we're creating, to manage the applications, a distributed management system called FogMan. So next slide. And what FogMan does, after you've deployed Eve and you've deployed and now are managing the hardware through the virtualization of ZEDEDA, you can now load these new applications running all those different south and north connections that we just talked about. So how do you actually load those applications? How do you update and delete those applications? How do you distribute machine learning models? How do you manage and back up the configurations of the connectivity, the IP address, this security key connected to this security trust that might be the Google, Azure, or the AWS of the world? So FogMan is our centralized management system to manage the application layer of these distributed networks. And one last, so here's a use case of an example that's worth noting. So this was a use case we did with Nokia and OSIsoft, and this was in the doing predictive maintenance on the wear and tear of bearings in wind turbines. Turns out if you put an amperage, a current sensor around the pitch motor, which actually adjusts the pitch according to the wind in the wind generation, you can effectively predict the wear and the tear on the bearings. So we put a current sensor around the pitch motor. We measure that over time and send those values to OSIsoft's Pi server. Next slide. And by keeping track of that time series data for each and every pitch motor, using the current transmission and distribution system they use to monitor the entire grid, OSIsoft Pi server, next screen, the utility is able to predict wear and tear on these wind turbines using the current operational systems that they've been trained on for the last 20 years, using modern IoT technologies with open source tools. Chris?
Thanks, Tom. So I'm going to pick up the pace a little bit because we're running just a little behind. But just while we're on the logo slide, let me, a lot of people haven't heard of Dispersive in this forum. We're new to the whole ZEDEDA ecosystem. So with that, we are ultra secure virtual networking. If you've heard terms like SD-WAN, software-defined WAN, secure access to the service edge, also known as SASE, or ZTNA, and I've heard a number of these mentioned in other pitches today. These are all just very descriptive of what Dispersive is and what it does. We do all those things and beyond. More specifically, we were engineered to reach all the way down to the IoT level. So we run on devices. We're in the Apple Store, for instance, Android. The smallest form factor we run on is a Raspberry Pi 3B. And with that, we're deployed on smart meters and lots of different things that are very relevant to the energy sector, rigs, and of course, all the different DER applications. A little more about what Dispersive, what the product actually does. So at an application level, let's say it's a DER application or SCADA data that's being communicated back up to an ISO or utility. We're actually going to take that data and break it down at a packet level and then channelize and disperse that application traffic across different channels, different lanes across the network. And open internet, by the way, is fine. Direct internet access, those things are all fine. So what happens there from a security point of view and privacy is there's no longer a single place that anyone could intercept the entire traffic lane. And so thus it becomes very difficult to hack and create problems on the grid, at least on that end. And then while we're doing that, we have built-in optimization, encryption. Again, it's built with zero trust network architecture, highly resilient. So if there's attacks or things on the network, we're able to respond to those and move traffic away from those things. And this is all, again, over the public internet, LTE, lots of different methods. We're pretty agnostic to communications with huge savings over things like MPLS or private network choices, private LTE, et cetera. So next slide, if you don't mind, we'll start getting into specifics around our friends in the energy sector, and you can go ahead and build this whole thing out. I'll just spend a minute walking through, some of the details. Having traveled around and spent a lot of time with ISOs and utilities and the DER participants, we've seen a lot of things. The participation we've had has been mostly on the SCADA side, but the communications and protecting the communications actually services the commercial entities and all the things they do as well. So if you think about this, it definitely applies to the balancing authorities, the ISOs, the utilities, as well as the very active areas we are in DER programs, the participants, as well as the smart grid suppliers of technology that goes into those programs. And that's where we'll embed our product and so on. So as you look across the slide, though, some of the big challenges, we've touched on some of them, but the things we're seeing is this expansion to solar farms, wind farms, hydro. They're voluminous. So they're smaller production of energy per site than what they're used to doing with, let's say, a natural gas generator or rig, and thus they have to have more of them. So what we're watching is SCADA connections, and a lot of these companies are having to manage the grid go from 500 connections, to 5,000 or more. And then when you start adding storage facilities, batteries, and backup power generation, it gets to be even larger. So with that, the threat surface of what people are worried about is expanding, right? You've got more points of penetration, more participants, more things that can go wrong. So with that, there's more attacks. There already are a lot of attacks and a lot of people assessing the grid for vulnerabilities. And so as Dispersive comes into play in this, we're making that less of a problem. And we'll talk about this more in a minute. But so the regulators and compliance bodies are upping the ante. They're trying to create better standards, but they're still not fast enough. Standards and changes to standards is a very difficult thing to implement. So and with that, we're also seeing a challenge. Just IoT, I think, is a key element of helping to drive costs out, but it's a challenging area to get it deployed and get these programs underway. So, and then, kind of last couple points on this is that while all this is going on, people are trying to simplify these, networking schemes, the administration, security, management of the whole program. And it's a real challenge. So if we kind of flip to the next slide, we'll take a minute to sort of talk a little bit more about Dispersive. So let me just, again, as I mentioned, and it's not showing up quite so well. It's faded out a little bit. But if you look on the left, just assume that's a DER location, and then it's communicating back over to the right. Let's say that's a utility or an ISO that's collecting SCADA data. Again, at the application level, we're actually, again, breaking up the SCADA data, that traffic pattern, and we're pushing it across the network. So if you kind of follow that blue line at the top, just a portion of the SCADA runs up into the cloud. There's a thing called a data deflect that sits up there, and that data deflect is constantly sensing traffic and anomalies. So if it sees an attack or a quality service problem, it'll actually move that portion of the traffic on that blue line in that cloud up top to a completely different cloud and a different traffic lane. There's one kind of in a plum color at the bottom. So it's resilient, it's self-healing, and it's able to defend itself. So a lot more to this in terms of encryption and layers of communication, but the really other cool thing is that we're boosting traffic and moving at a very fast rate, in contrast to things like VPNs that are much less secure and clearly slow down the traffic. I'm going to try to move this ahead just because we're running out of time. So let's go to the next slide, and I'll talk more about the use case for DER. So so we're very much focused kind of at the bottom portion of this, where you see the DER portion of generation. But we're also very much involved at the top with operations, and then the markets off to the left. So, again, we're taking the SCADA data, and we're taking this ecosystem of participants, companies that are generating power out in the field at these DER locations, solar farms, for instance, and then we're helping connect them up into the balancing authorities, into the grid management groups securely, so they can monitor and manage the sources of power that are coming in or available to manage the grid. So you can imagine having all these different participants and having them all interconnect and communicate. It's a heck of an ecosystem. And then trying to embed our products in and having them work with other products in that DER lane is a very important part. And then this is why it fits so well with IoT and the whole topics that we're discussing today. So the net is we're going to see more and more expansion of this. Customers are actually going to become producers of power. Where they're going to start, they are installing solar panels on their homes. They're going to have battery storage, and they're going to start feeding power back in the grid. So this is going to continue to explode. So I think companies like ours, OSIsoft, Dianomic, we're all going to have a lot of things to do to help with this transition to DER, and I'm happy to be a part of it. So with that, as the ecosystem grows, Dispersive is going to be there to connect it all together and keep it safe and reliable. So with that, let me pass it back over to Tom. And sorry I took an extra minute. Back to you. Oh, is Tom still here?
I am.
Oh, there we go.
Yeah. So was my apologies. Was that's the end of this? And were one of you guys speaking to any of these follow-on slides, or these are adders that we kind of went over at the beginning?
I think these are really meant to be a wrap-up where we kind of bring it all together. But I wasn't sure whether you were covering them or one of the other participants.
I wasn't. It wasn't. You can see where you guys fit in the stack and how we handle the remote orchestration of the hardware and software in it. But I think the idea was more to allow you guys to discuss your solutions and how they fit in. So
there is another slide after this that just talks to some of the benefits, I think. If it's still in the deck, so we could probably flash that up.
There we go. How's that?
Yeah, great.
So the summary of the benefits, backed by the industry-leading technology and service providers with domain expertise. You can see, everything's kind of detailed out here, applicable to many edge use cases as detailed by all three gentlemen in their presentations today. The ability to send data directly to multiple on-prem and cloud systems. Secure WAN overlay and distributed firewall enables secure connections and distributed energy networks. And importantly, the open orchestration API prevents lock-in. Open source Eve and the Fledge Foundation are part of the vendor-neutral LF Edge. Any of you gentlemen have any things to add to this slide?
Maybe we can just, if anybody has any questions that in the audience, if they want to type them in, we can answer any questions they have.
So I see. Okay, I don't see any.
Yep, I don't see any coming in either. So we
I don't
can
see any coming in. So I think we.
Yeah.
Thank you, gentlemen, for joining. I think it was very insightful, very helpful, and this will be recorded. The recorded copy will be available for everybody to download. And we'll go ahead and close the session out and move back to the sessions to join whatever other sessions you have an interest in.
Hold on.
Oh.
We got a question.
Will most of the computational power be required at the edge level? All right.
I can take part of that, at least from the virtual networking piece, but I don't know whether that's more applicable to Tom or Daniel.
Yeah, go ahead, Chris, and then I can add some more.
Sure. Yeah, I think so. Again, it kind of, this is one of those, it depends, right? Since you love answers that start with that. But architecturally, what we're hoping and what we're seeing a lot of in this area is where a lot of the smart grid suppliers are building some of that computational power into their smart grid products that go at the edge, that get deployed at the edge. And that's where a dispersive can be hosted inside the fabric of that smart grid product. If that's not the case, and I have seen that, we're also deployed on smart devices like Lantern boxes, which we're Lantern servers, edge servers that are either hardened or it depends on the deployment. But so in that scheme, that would be where most of the computational power is required, and that we would run at least that portion of the secure networking at that point, and then of course back up at the data center would be the other end. And then of course we'd have cloud compute for the cloud portion. So, but Tom, let me pass it over to you. It sounded like you had some thoughts on this.
Yeah, there's like 6 answers to it. So first one, if you look at DER, for instance, one of the new protocols being pushed, actually required by the state of California, is 2030.5. And 2030.5 is required for all inverters in DER. And when you actually look at the specification, it requires a policy engine that monitors the production of the electricity at the inverter. And actually, it will start doing control based on conditions. And all of that calculation is on the edge. So to implement something like 2030.5, you have to do it on the edge. That's how the specification's written. So there's an example. Another example in industrial, there's a common line that vibration is the heartbeat of a machine. So if you have any type of rotating equipment and you start using things like vibration telemetry data, and you put a 8 kilohertz vibration sensor on it, you should put it on the XYZ coordinate. That is 6 gigabytes of data per machine. You're not sticking that over your Wi-Fi. You're not processing that in any way whatsoever in the cloud. You have to do workloads like RMS, root mean square. You have to do FFTs. And if you think you're going to be doing machine learning, running TensorFlow light models and so forth on the edge, those absolutely are new workloads that the edge will have to take on.
Great, thank you. Well, it looks like we're.
I agree.
Go ahead.
I agree with the answers. I think you want to do computation as close to the data, the origin of the data as possible. So I think we're going to see computation moving towards the edge. But again, it depends on the use case. So some use cases can only be run in the cloud, for example. But I think we're going to see a tendency towards the edge in the future.
Great.
We got another question. Do we still have time? Or
we have about 30 seconds if somebody wants to field it from the business perspective. How open utilities to IoT approach while they used to rely on the specific SCADA-like systems?
Yeah, actually, one of our use cases, Jacksonville Energy, it's public. It was amazing that their $1 million transformers and substations were not connected to Emerson. And the reason they weren't connected is it was over $6,000 per point, and the price was just way over the top. And the people that really wanted to look at that data was the maintenance team, not the ops team. And so with maintenance driving it, they needed it actually going to Oracle system, and that drove the whole IoT rollout at Jacksonville Energy on maintaining a $1 million transformer.
Pablo, they are very cautious. There's no question. So you have to kind of prove yourself in. And I agree with your concern. We know how to do it, though. I think all three companies have done pretty good work here. All right. Well, I think that's a wrap. Tom, thank you. Sorry.
thank you again to you guys for joining, and I'm going to go ahead and end the session. If everyone goes back over to sessions and picks the next one they want to join, and again, thank you to our guests and presenters. I appreciate you taking the time.
Thank you, Tom. Thanks, ZEDEDA.
Thank you for organizing.
Thank you for having us.
Thanks.
Yep.